So as Phil said, I was going to talk about text classification today, and sort of just as an advance warning, and I know you've already had sort of the mass is your friend and numbers are your friend kind of lecture and all of Phil's lectures, so this is going to be much lighter on the mass than the other things. It's much more about sort of using some of the things that you've already learned in this course for a particular task, namely text classification. So roughly a couple of the things we'll talk about today is sort of generative and discriminative models. We'll look a little bit at naive Bayes and logistic regression, which is sort of text classification models or general classification models that we would have used independent of deep learning. Then we look at sort of different ways of representing text, softmax classifiers, and also some practical aspects of classifier training. All of that sort of hidden under the sort of umbrella of deep learning for NLP. So let's start with that. So all of you have probably seen emails like this before. And hopefully none of you have sent this guy any money because, that would probably disqualify you from being in this course instantaneously. But yeah, so text classification is, for instance, important for this. So all of you will have a spam filter somewhere in your Gmail account or email. And what this does is essentially text classification, reading a text, sticking a label on it. Is it spam or is it not spam? So this is just one example for text classification. And there's a whole list of things. So, is this email spam? Given movie reviews, is this a positive or negative review? So, Rotten Tomatoes, the scoring, they will look at reviews and automatically classify whether someone is enthusiastic about the film or not. Things sort of like identifying the topic of an article, predicting hashtags for a tweet, things like age and gender identification in reading documents, or related to that, actually plagiarism detection, as in, like, has this student actually written this essay or was this written by someone else? That's a form of text classification. So there's a whole range of different tasks. We'll sort of cover this slightly removed from the tasks thing, but more specifically in terms of the different types of classification tasks. So things like spam identification, a binary classification. You have two labels, you just need to figure out, is this spam or is this not spam? Then there's multi-class classification, where you have a set of, say, classes that a particular document can have, and you need to identify which of those classes it is. Multi-labeled classification is the extension of that, where a given text can have multiple labels, so not just be part of one class, but be part of several classes. And then finally, there's clustering, which is sort of the idea that you try to basically group a bunch of documents, but you don't know how to group them, so you try to sort of learn the structure given the data that you have. We're mostly going to focus on multi-class classification, but I'll try to talk about all of these things throughout the lecture. So, how can we classify text? There's broadly three ways you can do this. One is just by hand. The second thing is rule-based. The third thing is statistical. And all of these things do exist. So if you think of something like Yahoo in the old days, that was classification, manual classification by hand, looking at a website, trying to figure out which category should this be in our directory. And this is great in the sense that it's super accurate. It will be super consistent in terms of its classification, assuming the classification is done by experts in that domain. The downside, of course, is this is extremely slow to do because you have a human in the loop. That will also make it very expensive and means it doesn't really scale. So one step up from that is rule-based classification, where, so for instance, when, something like advanced search criteria is a type of rule-based classification if you want. The constraints say I only want to have results that are come from, say, CUK. That's sort of a hard-coded rule, and you know exactly sort of what to look for in a website on whether or not to sort of put it into that class or not, whether to return it or not. And again, this is nice in the sense that it's very accurate if the rules are suitable to your task. The downside is that you need to manually build and maintain this rule-based system. So if you want to add a new criterion, you need to come up with a new rule for that. And so the third category, and that's the one that we're most interested in here, is statistical classification. So here the idea is that we automatically learn how to classify the data. The upside is by letting the computer do the lifting for us, this means it can scale well. If we set it up well, the accuracy can still be very high, and the whole thing is automatic, which is always nice. The downside is, now this requires classified training data, so we need training data where we have both the document we want to classify as well as the label, the class label we want to associate it with. And depending on the type of model you're looking at, this could be a lot of data, so there's sort of that caveat. So, a bit more formally, so assume you have text represented by a label D and some class C. So what we want to learn is the probability of that document D being in class C. So this is actually really easy. This is all a classification is. It's just one little probability. And the two key questions are, first of all, how do we represent D? How do we represent a document? And subsequently, given that representation, how do we calculate this probability of C given D? So really, you can think of classifications as a two-part process. The first part being this representation learning exercise of trying to learn some representation D given a text document. And second, then the classification part where you want to classify this document given that representation. So how to learn P of C given D. I'll sort of try to vaguely structure the rest of the discussion along those two phases. So, as I said, the first thing is how to represent text. And again, there's a whole range of ways you can think about this. So the easiest would be you just take the text as it is, so like a long sequence of words. It comes with all sorts of downsides. First of all, that this is variable in length. This is sort of really hard to put into any kind of statistical model, and it's generally a bit of a pain. The next step up from that is you say, okay, let's forget about the sequence. We just treat this as a bag of words setup. So you literally just take all of the words in your text, in your document, and treat them as a set rather than as a sequence. The good thing is there's no effort required in learning the representation that's given. A downside is, again, there's some degree of variable size in there, in the sense that you will still have a various number of words in there, and it completely ignores the intentional structure because you just threw away the sequence information. The next step up from that is sort of handcrafted features, where you essentially have full control of what that feature what that feature could be. You can make full use of the NLP pipeline that you might have for extracting features. So something like getting a feature, whether you have this particular verb as the verb of this particular noun phrase, and you can build very class-specific features. So this is great in that sense. The downside is these kind of handcrafted features tend to end up being over-specific. They'll end up being incomplete, and they make use of the NLP pipeline, which is of both an upside in the sense that we have this nice pipeline of various NLP mechanisms, parsers, chunkers, and so on. The downside is that all of these things will be somewhat lossy, will be somewhat inaccurate, and so you sort of propagate this, whatever area you introduce up in the pipeline, down into your classifier. And then the third alternative is just to say, well, let's learn the feature representation. So instead of handcrafting features, let's just try to learn a representation that automatically gets all of the relevant information we need from the text and passes it onto the classifier. So that's obviously nice. The downside is it's a learned representation, so we need to find some way of learning it. The second thing, quickly before we get into the actual models to talk about, is the distinction between generative and discriminative approaches. So a generative or joint model tries to model a probability of C, D. So it's the probability of the individual classes together with the documents. Or the probability over both observed data and hidden variables, where the hidden variables are your class variables. And like a lot of models, if you've taken the machine learning course last term, would fall into this category. So n-gram models, hidden Markov models, probabilistic CFGs, or the IBM machine translation models, all of those fall into this category of generative models. The second variant is conditional or discriminative models, where we just want to learn this probability of C given D. So the difference here is that we sort of assume that the document is there. We don't put a probability on this document existing, we sort of just take it at face value. And so what we do here is learn boundaries between classes. So we take the data as given and only put a probability on the hidden structure given that data. And so models for that are things like logistic regression, maximum entropy models, CRFs, support vector machines, and so on. Again, you probably would have run into a couple of those last term. So let's start with one classifier. So a really easy one. I'm sure most of you have sort of come across Bayes' rule. This whole idea of probability of C given D is the same thing as probability of C given D given C divided by probability of D. And so this is great for modeling a conditional probability, where we're interested in this case in C, but we have a lot of information about D. And in fact, because we're only interested in classification right now, we can ignore the denominator, so we don't need to put a probability on the document's existence. So we end up with the probability of a class given a document being the same thing as of the prior probability of that class times the probability of that document given the class. And we can make this even easier by saying, well, we're going to split the probability of the document given the class into the probability of every single word in that document given that class. So this is the last row here is a probability of C times the product of the probability of Ti, where Ti is an individual word in a document given that class. This is really nice and also very easy, because now we've sort of broken this harder task of getting a class out of a very long document into a much easier problem of assigning the probability of a given word assuming a class. And when you think about the two terms we have in there, so PC and P of Ti given C, it's actually really straightforward to estimate both of these probabilities given some sort of training data. So the probability of a given class is literally just the number of times you've observed that class in your training data divided by the number of documents in your training data. So say you have a big set of movie reviews and 500 are positive and there's 10,000 overall, then the probability of any review being positive is sort of 500 over 10,000. The second probability is then the probability of a token given that class, and that's sort of the same counting game. So again, you just take the number of tokens in that particular class that are of that type, divided by the overall number of tokens in that class. So, for instance, if you have the word bad, and you want to get the probability of the token bad given a negative review, you see like, okay, in all of my negative reviews, bad appears 20 times, and there's 5,000 words overall, so it's 20 over 5,000. This is great because this requires no training whatsoever. It's literally just counting tokens and dividing them. Now, one important thing here is that we simplified this earlier, right? So we turned the probability of D given C into sort of this product of the probabilities of individual tokens given C. And this is sort of why it's called a naive Bayes classifier, because we make this pretty naive assumption that all of these words are independent, that they're independent of their position in the document, that they're independent of each other. And it's sort of a pretty strong assumption to make. Oddly enough, it actually does work in a lot of cases to still classify by throwing away all of that structure. When you think about something like reviews where you just want to get sentiment, there'll be a lot of words that you just inherently associate with something positive as opposed to something negative. So there'll be pretty strong markers regardless of the context they appear in. Or assume you want to classify newspaper articles and figure out is this politics or sports or celebrity gossip, right? Then, like if it's something, if the word football appears, that's a really strong signal that this is probably sports. And if it's something about Davos and economics and so on, it's probably not celebrity gossip and so forth, right? So, it's called a naive Bayes classifier. It's actually surprisingly robust. Now, so given all of these things, what we actually want to find out is, given a document, what class should I give it? And the way you do this is you take the maximum a posteriori class. So that's the class that maximizes the probability of P of C given D. So essentially what you do is you take the argmax over all the classes for that particular probability, and then you can divide this up into sort of this product of the class prior probability and the product of the individual term probabilities. And you literally just find which one is the most likely by sort of plugging this formula in and computing it for every single class in your data set. Now, one catch is that if you have long documents, multiplying loads of small probabilities is really bad because at some point your computer is going to underflow. And so one way to avoid this is to just move the whole thing into log space. So when you put the whole thing into log space, you can sort of just take the log probability of the class added together with the sum of all the log probabilities of the individual words. That's the other nice thing about log spacing things. So you get rid of the multiplication and you replace it with addition. The other thing that's bad is zero probabilities. So in the in the original case, if you had any word that never appeared in your class, that probability would be 0, which means the overall probability will be 0. And likewise, once you're in log space land, if you have a 0 probability in there and you try to log it, then, well, you know what happens. So one way to get around this is to add smoothing. And literally, the most easy way to add smoothing is so to take this probability of t given c and add 1. So you take the probability, and in the new equation, you basically add 1 to the token count, and you add sort of v, which is sort of your vocabulary size to the denominator to keep the whole thing balanced. So this is called Laplace smoothing or add 1 smoothing, which is sort of the more intuitive name. There's been tons of research into alternative smoothing techniques, which you could look into if you want to, but this is a reasonably safe bet to go with. So, in sort of conclusion for naive Bayes, what are the advantages? This is super simple. This is completely interpretable. And interpretability can be important, right? But this is beautifully interpretable in the sense that you have the probability of a particular word belonging to a particular class, and when a decision is being made whether to associate a particular document with a given class, then you can literally just look up, okay, which of the words pushed my classifier into the direction of that class, which other words pushed me away from that class and actually preferred a different class. Sorry, you had a question?
Can you just explain again the PC, P, T given C on the slide before, like definitions?
Here.
Yeah, these two.
Okay, so PC is the probability of a class. So assume you have sort of a task where you want to classify across 5 different classes. This is the probability of choosing a particular class. There will be some scenarios where all of the classes have equal probability, but in a lot of cases, some classes will be much more heavily preferred than others. So, you know, if you take something like the Financial Times, you want to classify it, there'll be 90% chance it's politics or economics, and only 10% chance it's celebrity gossip, say. Okay, so DC here is the, like assume you have a training corpus, which contains documents. Then DC is the number of documents in that corpus that belong to that class. And the D in the denominator is just the overall number of documents in your training corpus. So if you have 300 documents of that class out of 1,000 documents overall, then the probability of that class is 30%. Yeah, exactly. All of naive Bayes is extrapolating from the training data you have. You look at training data, collect statistics from there, and then based on that, sort of make these assumptions about probabilities of a class and probabilities of tokens given classes. And for the second thing, it's exactly the same logic. So here this is again the count of tokens that are associated with class T and are of type lowercase t. And you divide this by the overall count of tokens of that type in other classes. All right. So yeah, simple, good. Interpretable, also good. It's also really fast, which is nice. So it's linear in the size of the training data. You just need to go through it once, collect all of the statistics, and so if your probabilities will fall out of that. And it's also linear in the size of your test document. You just need to go through all of the tokens in your document. You get the probabilities for those tokens given the various classes. You take the argmax. The downside is this independence assumption that you made. So by saying we ignore this intentional structure, we just take the bag of words. In many cases, this is actually too strong. So this might work well in something like classifying newspaper articles, where you have sort of a couple of trigger words that will strongly inform your model. But it can go horribly wrong in, for instance, sentiment analysis. You could have something like, this movie was the worst, blah, 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 except for all the other films I've seen last year, which kind of then is a positive review, but you've got all of these negative trigger words in there. So this independence assumption can sort of mess with your model in many cases. Second point kind of follows on from that, so the sentence document structure is not being taken into account. And then there's the whole thing about zero probabilities, which sometimes is awkward. because you encounter them, and then the smoothing can also mess with your probabilities a little bit and give you undesired effects. So that's just something to bear in mind. So, we started the whole thing off by talking about generative versus discriminative models. Would you say naive Bayes is a generative or discriminative model? Should we do a show of hands or something like that? Who thinks it's generative? And who thinks it's discriminative? That's disappointing. So yeah, the majority of you were right, obviously. It's a generative model. I was kind of hoping everyone would go for discriminative. That sort of seemed like an easy way to trick people. Oh well. So I mean, we've got this discriminative probability we talked about the whole time, probability of C given D. But when you look at the overall model structure, actually, we have this sort of complete set of probabilities in that space. And so what we overall model is the joint probability of documents and classes. So while we use this conditional probability for classification, we have all of the information in the model to sort of trivially invert the process and also generate data from that. So you could see quite easily if you took a particular class, how you could randomly generate new documents that fit into this class just by sampling words that are likely under that particular class. That's kind of why this makes it a generative model. Also, it's sort of, honestly, it's a reasonably poor man's generative model.
So it makes it interpretable too? Are most generative models more interpretable because they break code?
I mean, that's one way of interpreting a model, I guess, by generating new data given a class. I think in naive Bayes, it's mostly interpretable because you have these very precise, easy to look at probabilities. Where you say, okay, my classifier said this is a negative review. What are the most negative words it found in there? What are the most positive words it found in there? Like out of those 20 words, my classifier thinks these 8 talk about sports, these 4 talk about the economy, and these 4 I don't know what they're about. Like that makes it really interpretable in my mind. Sure.
You have in the previous slides this variable capital V, which is probably
This guy here.
Yes, and in some other slides as well. This is presumably the vocabulary.
Yeah, this is a normalization constant, exactly. So yeah, V is the vocabulary, so that's the number of different words you have in your corpus. And so for instance, when you do add-one smoothing, in order to keep these things as probabilities, you need to balance out the one you add up here by dividing by an appropriate number, and seeing that this is the probability of a particular token, of a particular type, you divide it by the number of types you have in there, which is the same thing as the size of your vocabulary.
So there is a modeling choice to be made to pick the size of the vocabulary you're going to look at in the first place.
Well, it's sort of informed by your training data, right? I mean, so what you would typically do is you have your training data, say you have some 10,000 documents with labels, and then you get the vocabulary out of there. What you'll end up doing in practice is you'll end up removing stop words. So you'll have some list of words that don't hold any sensible meaning, something like and, then, or pronouns, function words, these kind of things. And normally you would end up removing them just as an efficiency play. So you have some sort of degree of modeling freedom of how big your vocabulary is. But it's mostly informed by your data. Cool. Feature representations. In naive Bayes, obviously the feature representation was a bag of words. So you just take every single word and you look at all of these independently. And you can also think about it slightly differently. And like as you see, I'm sort of slowly moving into sort of the vector space modeling side of this lecture. So you can think of a text representation or feature representation of text as a vector where every single element indicates the presence or absence of a particular feature. And so features could be binary, just denoting presence or absence of something. You can have multinomial features where you, for instance, count the presence of something. So you count the frequency of a given word and document, for instance. And you could have continuous features, something, for instance, TF-IDF weighted features, where you sort of weight the frequency of a word divided by the frequency of that word in other places, these sort of things. So assume, for instance, we have this kind of feature vector here. So we have 6 features. The first one is just a bias term. The second one is sort of checking whether the word Prozac appears in your text. The second one was a school. The third one, dear friend, and so on. And we associate different weights with these features. Positive weights pushing the classification into one direction, negative weights into the other direction, assuming binary classification. So I guess just looking at that feature list, it's probably pretty easy to see what we're classifying here. Yeah. And this is actually fun if you're sort of bored after this lecture. Have a look on your laptop, if you have a Linux laptop, if you have Spam Assassin installed. So they actually have a feature list for classifying spam. And when preparing this lecture, I looked at other people who gave the same lecture. Someone actually bothered to copy over these features, and that was 40 slides in really small font. They have several thousand features just for classifying spam, all of them sort of gently nudging the decision one way or the other way. Which kind of brings me back to this point of handcrafted features. You can get really carried away with them if you try to make this as general as possible. You'll just end up with tens of thousands of these guys. But let's just assume we have this feature representation for the time being, and what can we do with that? And one way to use feature representations to classify text is logistic regression. So we're going to throw away all of this generative nonsense, and we just say we want to have a nice, clean discriminative model. We just want to learn the probability of a class given a document. And so one way to do this, as I said, is a logistic regression. It's called logistic regression, logistic because it uses a logistic function, and regression because it combines a feature vector with weights to compute an answer. That's kind of all there is to it. So in the binary case, this looks like that. We have 2 probabilities, the probability of true given a document and the probability of false given a document, or stick in whatever labels you want. And the first one is just basically 1 over 1 plus the exponential of the bias term, beta 0. I had that in the last slide, if you remember. And the sum of all the other features, so basically combining their weight and the actual value of that feature given a particular document. So here now we take the document D represented as this vector x, where xi indicates an individual feature and whatever value that feature has in that particular document. Then there's also the multinomial case, so that's the one where we have more than one class we want to decide about, but it's actually sort of a choice between several competing classes. It's pretty much the same function, except that now we don't divide just by this one exponential given a particular feature weight for a class, but we assume that we have sort of these beta terms for every single class in our list of potential classes. So if you want a probability of a class given a document, say it's class C, then you take up here the sort of the term specific to that class, just like here, and you divide this by the sum over the same term for all of the competing classes, including the class itself. The denominator here is important because that means that the probability, it's important because it means that this value across all the classes will sum to 1, meaning that we end up with a probability distribution. And probability distributions are nice because, we'll always get a value between 0 and 1, and we can do all sorts of fun with that. So to get to the logistic part, up here it's the same two equations again. You can kind of look at them in a more simple notation by just saying, okay, we sort of take this value, we get like this beta I, xi computation, and just replace it with a single variable. And then you get the formulas below here. So probability of C given D is just 1 over 1 plus exponent minus Z, or alternatively, the exponent of Z of that class C divided by the sum of the exponents of ZZ for all of the other classes. I'm just putting this on here because that's how you end up with the logistic function. So the function on the left here, that's what's called a logistic function. On the right-hand side here, that's the softmax function, which is of the multinomial extension of the logistic function. I put a small disclaimer here. So it's kind of the correct form, but it's not necessarily the most general form of expressing a logistic regression model. But for the purposes of what we're discussing here, that's sort of a sensible form to talk about. If you want a more complex variant, look it up on Wikipedia. But I recommend you save yourself the time. This is the one that you want. So logistic function looks like this. And the key bit here is that, as I said before, whatever value you give it as an input, you end up with an output between 0 and 1. And the way that we set it up with sort of the positive function here and the inverse of that means the two values we get out of this will sum to 1. So we end up with probabilities. The softmax kind of looks like the same thing, except that it's a multinomial generalization of that thing. So the shape will look a little bit different depending on the number of classes you have. But again, the great thing here is we can sort of take the output of k distinct linear functions, where they can be of any size, of any value, and as long as we squash them all together in a softmax, we'll end up with a probability distribution. Cool. So given this model formulation, I want to learn these parameters beta, the weights that I showed earlier for the spam classifier. And so the way we would do this is by maximizing the conditional log likelihood of the data according to the model. And so due to the softmax function, we don't only construct a classifier, but we learn probability distributions over that classifier. I keep saying that, but this is really important. You really want to end up with probabilities rather than sort of independent numbers that don't sum to 1 and give you any sort of unbounded likelihood. And now there's a ton of ways you can learn beta. You probably covered a couple of those in the machine learning course. So I'm going to skip over most of that quickly, but like ways to think about it, like you could use a perceptron for that, where you just find misclassified examples and sort of gently nudge the weights of beta into the right direction to push that particular example to be closer to the class it's supposed to be in. You can look at various margin-based methods, such as support vector machines. But also, like because we talked about logistic regression, you can just directly maximize the conditional log likelihood via gradient descent. So the conditional log likelihood is the following guy. This is essentially the same equation we had before, just we moved the whole thing back into log space again. That's sort of a recurring theme. It's just much easier to deal with. And the great thing about log space is we can move the log inside of that product, which then gets replaced by a sum. So the probability of a class given a document and variables beta is the sum of the log probabilities of that class and that document given beta. And now, if you want to sort of open this up further, again, you substitute in back the actual equation we had for this probability, so you end up with this guy here. And now in order to learn beta, you just have to take the derivative of that function with respect to beta and sub in the values you get. Now, the good news is the derivative for this is concave, so there will be one best set of values or a couple of sets of values that are equally good, but they will be in the same space. So you're bound to find them if you look hard enough. The downside is there's no known closed form solution, so you can't directly compute them, but you have to approximate them, learn them via something like iterative gradient descent, which I hope Phil covered already. If not, then I'm going to leave that as an exercise. I don't think that's worth deriving today. So just like naive Bayes, in summary, for logistic regression, the upside is this is still a reasonably simple model. The results are still very interpretable because we still have nice probabilities that we can look at. We have these weights we learn with a given feature and the betas for the different classes that will inform us sort of what influenced the decision to pick a particular class. And because now we pick the features ourselves rather than using a bag of words, we no longer assume statistical independence. And this is really important because now you can learn combinations of features. As in, this particular class is likely if that word appears but not that one, and these two things appear, but if only two of those three appear, then we want a different class, that kind of stuff. Main drawbacks here is this is a lot harder to learn than naive Bayes. If you remember earlier naive Bayes, it's that you just read the text, write on the probabilities, you're done. Here we have to do gradient descent and we have to calculate derivatives and all of that. The second downside is that manually designing features can be expensive. So, Spam Assassin with their 60,000 features, that must have taken a lot of time and work and money. And related to that, again, you have this issue that handcrafted features will not necessarily generalize well. So you might learn all of these features for your one classification problem of figuring out if a Daily Mail article talks about cancer or not, but then this really doesn't help you for training the same classifier on figuring out whether DFT talks about sports or celebrity gossip. All right, that's it for logistic regression. I kind of figured I'd need an hour to get to here. I was a bit faster than planned. Do you want to take a 5-minute break, or should we just power through? Power through. Awesome. There goes my cigarette. It's terrible. All right, so this was sort of classical text classification algorithms. This could have been a lot of repetition if you've taken a machine learning class before, an NLP course before. But it sort of kind of gives nice groundwork for the deep learning version of that. So I really quickly recap recurrent neural networks, which Phil covered last week. I think here prettier figures, but it basically looks like this, right? So you have some sequence of inputs X. You take a particular input, you feed it up through some function to get a hidden representation H, and from that hidden representation you get an output probability Y. And then you have this whole recurrence thing where, if there's a language model set, for instance, you draw a word from Y, feed it in as the next X, and then you compute the next hidden state given the previous hidden state and that new input. So far, so good? Awesome. So,
The output goes back to you when
it depends on what you're doing. If the output goes back to the input in the case of a language model that you're generating from. So when you just have a start symbol and you want to just randomly start generating a sentence, you sort of take an output probability, you draw a word from that probability, you pretend that was your next input. When you train a language model, of course, then you still get these probabilities because you use them to get your error signal, but you don't actually use them to inform the next word.
Do they normally pass in the whole distribution, like all the output nodes on the previous step into the next one, or is it usually sparse?
No, so if you do this in generative case, what you do is you take this output distribution, which is a distribution over the vocabulary. Yeah, that would be vector, like a probability vector, and then you draw from that. So you draw a particular word, and then you feed in that word, which then means if you basically you draw some word from this vector, and then what you actually feed in here is just that word for which you then look up the embedding in your input dictionary, in your input embedding table. Yeah, cool. So that's a recurrent neural network language model. I hope you remember. And now we're gonna mess with this a little bit, but let's briefly think about the information contained in that. Right. So as we just discussed, basically Y, the Y vectors, what they are is a distribution over the next output word. But what's more interesting in my mind is the vectors in the middle here, H, because what they do is they accumulate state. So they accumulate the state over previous inputs. Because they sort of feed them both through time as well as from the input level. And this is true regardless of what kind of architecture you use. And you'll see I'm kind of ignoring all of the neural network dynamics here. Like you can stick in an LSTM, you can stick in a GRU, you can have a simple feed-forward network. It's all the same for the purposes of disk, as long as we have this one representation in the middle that captures state over time. So, as I just said, think of H1, Hi, as sort of a function of x from the start up to point I, and of the previous h's from the starting point to I minus 1. And so when you write down the mass and so if you manually enroll the neural network, you'll see that this is the case. So this means we could assume that Hi sort of contains all of the information of the text up until that point. And so we talked a little bit about how to learn representations for a given document. X before, so we had the bag of words idea, we had the idea of sort of manually designing features and looking up whether they exist in the document. But H is kind of exactly the same thing as well, right? That this hidden representation, H, is a representation of the text you've just been reading. So this is great because we get our text representation for free. So back to logistic regression. Revisiting is a bit silly now because we didn't take a break. You'll probably still remember this. But basically, like X here, the representation of a document within logistic regression is, we can set that to just be h of n, where n is the length of the document. So you have an RNN, you read in all of the text, you have all of your hidden representations, you accumulate all of that representation over time, and then bam, at the very end, you have hn, and we'll just pretend that this captures all the information that we need to know about the text. And so this is great, right? Because now we can stop. We're done. We've got Phil who explained to you how to build an RNN, and now you've read up everything up, and now we've got a hidden representation. We just say, hey, this is our feature vector. We plug it into logistic regression as before. So look, I replaced the x's with hns, and we're done. And we can stop. This is nice because now we have the RNN to read our text and logistic regression out of the box on top, and we can classify whatever classes we want to find over this document. In fact, we can use any other classifier on top of H as well, right? Assuming you don't have labels and you want to cluster the whole thing, we just stick that vector into a k-means classifier. You can do whatever you want with this guy. Now, the one catch is that I kind of said, H will capture everything we need to know, but how do we actually make sure of that? How do we make sure that H actually pays attention to relevant aspects of the input text and doesn't just forget about it and doesn't just approximate some cheap n-gram model and maybe just remembers the previous two words and ignores all else? The trick for that is that we just move the classification function inside of the network. So we've got the same RNN as before, but now we say at the end, let's feed this guy directly into a prediction model that predicts the next class. And more concretely, the way this looks, sort of related to your question now, we can throw away the outputs because we don't care about those. We're not trying to model the language here. We're just taking the language as it is. We just want to learn those hidden representations. And then we stick something at the end here, which could be logistic regression, for instance. More concretely, the way this would look is we say, okay, let's take hn as the input to our classifier. So we set x to be hn. Then we compute the class weights. So that's the term you saw earlier within the exponent, within the exponential. So f of c is the sum over all features, which is now the dimensions of that vector, which have a feature weight beta that is dependent on the class and the individual feature and the input xi. Next we're going to apply nonlinearity, which I think Wang probably talked to you about earlier in this course. So this is just something nice that gets all of these representations back into sensible space. And finally, we stick the softmax function on it from, again, earlier. So we get a probability of a class given a document by dividing the exponential of MC with the exponentials of MI, where I is any of the competing classes. And that's it. So sort of in neural network speak, this would look a little bit like that. So we have our input vector D. We do this matrix vector product to get our feature representations per class. We apply the sigmoid function component-wise. And finally, we stick the softmax on top, which will then give us an output probability distribution.
So as I understand it, the softmax is the multi-dimensional generalization of the sigmoid. So what's the value of defining the sigmoid and then the softmax, given that the softmax is already nonlinearity?
They have two different functions here. So the softmax up here basically just takes some value and makes sure that we end up with a probability distribution. The sigmoid here, which we apply component-wise, so this is slightly different because this is not comparing a particular weight with sort of all of the other weights, but it's just moving that weight in itself. This is important because it allows us to model nonlinear functions. So if you can take the sigmoid out and you'll still get a classifier. That's purely optional. It's the difference between having a linear classifier and a nonlinear classifier. And basically having that sigmoid in there will allow you to model richer distributions. And in fact, you can also stack these guys up. So nothing is stopping you from just having one set of features in a sigmoid and a softmax. You could do this repeatedly to model even more complex functions.
So the LSTM or GRE or whatever you pick by itself isn't enough to create interesting nonlinear stuff. It's factors best.
Yeah. Basically, yes. In the sense that, again, you have different functions there, right? So the nonlinearities in the LSTM say what they're concerned with is building up the state information, HI.
And the state is
But the state is not necessarily tuned to just taking care of this classifier. We'll get to this a little bit when we talk about how to train these things. But basically, like this hidden representation H will have to fill a couple of roles. The nonlinearities have to make sure that you don't lose information over time, for instance, that you don't sort of vanish your gradients and not train the beginning of the sequence, these kind of things. Whereas the nonlinearity here allows you to classify more richly.
well, so in your head, intuitively, do you think about the hidden states as being linear or nonlinear? Like actually the cell?
Well, not nonlinear. Yeah. So, yeah, basically the last slide, we've probably seen all of the maths for that before earlier in this course, because essentially what this is a multi-layer perceptron. That's what we just talked about with these questions. It's a nonlinear way of classifying things. I don't know how this was explained, but for instance, an MLP is nice for solving problems like XOR and things like that, where you don't have enough features to solve this with a linear classifier. So you could sort of do the kernel trick old school, or you can use an MLP more recent school. And so yeah, given this MLP, what we want to optimize now is the whole network together, so that we make sure that H carries the relevant information for us and that the classifier gets trained suitably. The way to do this is you can model this using a cross-entropy loss. And that's basically just this loss term. So you take this YC here, which is set to 1 if this particular data point is of that particular class C, and it's 0 otherwise. And what you want to optimize is sort of the negative sum of these guys, so basically the negative log probability of the true class given the document. And again, if you then open this up, it looks like that. And that should look oddly familiar from the discussion of logistic regression earlier. So cross-entropy is a nice loss because it's basically designed to deal with errors on probabilities. This is where probabilities become important again. And optimizing here means minimizing the cross-entropy between the estimated class probabilities, that's our term here, P, C given D, and the true distribution. Where the true distribution is against of the distribution that we assume is inherently true of the data. So in case of the, if you think of this probability being a vector of probabilities for different classes, for labeled data you would assume that this is a one-hot vector, which is 1 for the true class and 0 for all of the other classes. And so we're minimizing the distance between what we're estimating and so of that true class for the data points where we know the class label. And again, there's sort of tons of other alternative losses you can think about employing here. Things like hinge loss or just normal squared error, L1 loss, and so forth. I'm not going to get into those too much. I think like this is sort of the obvious loss that you would want to take when optimizing this. But again, in the sources, we'll have things for you to read up on the others if you're interested.
A little bit more detailed questions. Would you typically combine a recurrent and non-recurrent, let's say an LSTM and one layer to sequential layers?
So can you say that again?
Would you typically combine recurrent and non-recurrent layers in a neural network to a text-specific class plane, say LSTM and then standard class layer?
Well, for things like this, yes. In the sense that the recurrent part of the network here is taking care of dealing with variably sized data and effectively sort of compressing that into one fixed dimensional representation. And then you can use the sort of non-recurrent, if you so one part, to then deal with that going forward. So yeah, I mean, this is what you would typically find in classification tasks and question answering these sort of problems.
So we typically have one recurrent layer at the input and then non-recurrent layer for doing further processing.
At the end, yes. I mean, it depends on the task, right? I mean, if you think about machine translation, for instance, there's nothing to classify, so you don't need anything that isn't recurrent. You want to generate something that's recurrent. But for any task where you want to classify something or where you want to generate a single data point, typically something like an NLP or similar classification model will do the job quite nicely.
Good question. It looks like during the first training you kind of did a classification at each stage, and then you kind of threw those out, and then only we could use the classification as the last recurrent node. Is that there are two training stages where you firstly train the hidden representations and then you do like some fine-tuning?
I think that's my next slide, actually. No, I'll get to it in a few slides. But yeah, basically, there's different ways you can set these things up. So in this slide here, the example was just you take the whole sequence and you classify at the very end. You're right, you could quite feasibly say actually you want to classify after every word or after every sentence or something like that, just so that we get a stronger error signal throughout the whole recurrent part of the network. And there's different ways you can code train these things, which we'll talk about in a bit. Yeah. All right. So yeah, that's the loss. And now there's a couple of extensions to that I was considering. So what do you do if you have a problem where, say, a single data point doesn't only have one label, but could have any number of labels? So this is something like what a lot of people have been working with, sort of like hashtag prediction given a tweet, or sort of Instagram where you have sort of different labels associated with something, or if you go away from language, something like image detection, labeling all of the objects in a given image. Now the problem is that cross-entropy loss assumes that there's only one correct label. So you need to modify this a little bit. And the most straightforward option for that is to replace the cross-entropy multi-class classifier with a series of binary classifiers. So basically assume that for every possible label C, you have this binary classifier with still its weights beta and so on. And then you get something that looks a lot more like the easier function we talked about earlier, where you just have two probabilities, true or false, rather than sort of a sequence of probabilities. And again, then you can modify that loss, the loss from the last page, to sort of get this longer joint loss, where now YIC is true if a particular document I is in class C and 0 otherwise. So a little bit like before. And then you have the sort of the positive probability of that and the inverse probability if it's negative. And the loss kind of looks a bit more complicated than the previous one, but actually when you take the derivative with respect to f, you get a super nice simple derivative, which is just the truth label minus the sigmoid of fc. So this is quite nice because this then sort of gives you a really nice loss term at the top of your classifier, and then it's easy to backpropagate this loss through the rest of your network. And now this sort of gets to your question. How else can you train these things? So something that makes sense in a lot of cases is to say, well, let's train the RNN not only with a classifier loss, but let's stick a language model objective on there as well. So you go back to having the full structure, so you have these predictions over Y, and you get a loss here given the next word, and you optimize this jointly together with the classification loss. And again, there's sort of endless variance on how you want to do this. You could say, well, we just train the language model for a long time, and then we take the trained language model, freeze the weights, and then we train the classifier on top of that. Or we train a language model, and then, so if you dampen the weights, so you sort of basically lower the gradients quite a lot when they feed into the language model, and you mostly train the classifier, but you still like slightly adjust weights in the language model. And also the other standard thing that a lot of people just do is sort of take pre-trained word embeddings and feed them in there at the bottom. I mean, that's sort of a way of code training as well.
Yeah, it seems like the language model and the classifier have sort of contradictory objectives, especially in terms of what they store and getting there. The language classifier or the language model cares mostly that, for example, the previous 5 words and all the written messaging, whereas the classifier looks at the text globally.
Yes.
That sort of, you have two contradictory practices in terms of what you're throwing in there.
Yes, that's partially true. So it's always a trade-off the moment you start introducing extra objective functions. But at the same time, the good thing with the language model is that it still learns a lot of things that you would want to use in a classifier. So with a language model, for instance, over time you'd assume you end up with similar representations for semantically similar words, just based on their co-occurrence. And that's something that's actually very useful for the classifier later on. If there's a word that you may not have seen in your sort of labeled data, But from the language model training component, you know that it's very similar to other words that you know and that you have a strong signal on. So that's kind of where this makes sense. And like particularly, that's sort of the point at the bottom here. The nice thing by having this dual objective is that you can make use of tons of data beyond just the labeled data. For instance, a couple of years ago, one of the standard sentiment training data sets was movie reviews from IMDb. And it was 500 positive and 500 negative reviews or something like that. That's not enough text to sort of learn sensible representations if you have a large model. But if you take that together with, say, 1 billion words from a similar related corpus that doesn't have labels, then you're talking, right? Then you learn sensible representations. And then the hope is that they will sort of not only make the language model stronger, but also inform the classifier. All right. So another way to make the whole thing stronger is bidirectional RNNs. I'm not sure if Phil covered them in last week's lecture, but if not, they're completely easy. So the idea is basically, instead of just reading text sequentially from left to right, building up the state, as we do down here, we also do the inverse of that. So we take the text from the right-hand side to left-hand side and read it backward. And you just take a second model, a second recurrent neural network with LSTMs or whatnot, up here, and you sort of compile a second set of hidden states. The update rules for this follows directly from the forward-facing RNN. But in practice, these guys have shown to be slightly more robust when then used for classification tasks. So the key difference here is obviously that once we have this bidirectional thing, the model is no longer trivially generative. In the sense we can't just generate because we have to sort of assume that we know from both sides what the previous context has been. So we can sort of generate a single word. And there's actually interesting word embedding learning methods that make use of this sort of bidirectionality. But if you want to generate new text, you can't do that because you sort of have to start at both ends and then sort of pray that your model kind of predicts what the other model previously predicted. And trust me, that doesn't happen. But they're really good for classifiers. Because now what we do basically with this bidirectional network is we say, okay, let's read in our text left to right, H0, H1, H2. Bam, that's a representation of the document. And now let's read the document again backwards, X2, X1, X0. We get this hidden state, H-0. And now we combine this guy here and that guy here as input into our classifier. That's sort of like literally the easiest way you can gain a couple of percentage points in whatever you want to classify. Just duplicate your recurrent network, feed it forward and backward, and then literally just concatenate the two hidden states. So now, say if your previous network had a hidden state of, say, 128 dimensions, now you have something of 256 dimensions. So the classifier has more information to play with. And this sort of also automatically takes care of a couple of problems of recurrent networks in the sense that assume the sequence was a lot longer, then maybe this final representation here will have actually lost quite a bit of the information from the beginning of the sequence. And by having the converse up here, you sort of cover both ends a little bit better, and by extension the middle ground as well. So that's just a nice trick to play with if you ever implement one of these guys. Quiz time again. So, simple RNN classifier, generative or discriminative? Who thinks generative? Who thinks discriminative? Awesome. Why did you pick something? That's not bad. I was going to go with either. Basically, they can be either depending on how you want to set them up. So what we talked about so far was discriminative in the sense that we take the data as it is, we just compile a state, and then we have the predictor. But what you can also do is you can turn the whole thing around, right? You can just say, okay, let's take this hidden representation that we feed into our predictor and use that to initialize a recurrent neural network that then generates data. And this is just as easy to train, right? We say we have this guy, which has to come from a particular class. And we know our document and training data, so we can train a language model just as you did last week. And we have the generative counterpart. So if you want a generative RNN classifier, all you have to do is stick these two things together. So you have your encoder, the class prediction model in the middle, and the decoder, the generative part. So with this joint model, you learn both the probability of the classes as well as the probability of the data. And once you have both of these guys, then you're in joint space.
Any comments on the advantages and disadvantages of that?
Well, again, it depends on what you want to do. I mean, there's something about interpretability in the sense that if you have this joint model that also generates, you can see what kind of things come out of my model in terms of text.
Oh, you tie the weights, or it's
That's a modeling choice.
oh, okay.
There's an argument to tie weights, it'll probably speed up training. There's an argument for untied weights, it might give you higher accuracy if you manage to train it for long enough. There isn't that much of a point to be honest, in this particular scenario. These kind of models will become really important in 3 weeks' time. That's why I decided to stick them in here today as well.
I have a question. Would we consider in this case to be also task-based, like the ones we were discussing?
Sorry, can you say?
Would it be here, like learning the actual representations, would it be here considered task-based if we do it that way?
It depends on how you train the model, right? So if you go with the version where you first train a language model to learn your whole recurrent architecture, then that part is task independent. Right? But then the classifier will be task-based in the sense that you train it on labeled data from a given task. So that's always going to be task-based. The recurrent structure depends both on how you train it. So if you train it fully jointly, there'll be a task-based component in there. If you train it independently of the classifier, but only on data of this particular domain, it'll end up being task-based. So you always have that component in there, I would say. All right. So this was sequential neural network so far. Read a text from left to right, or if you feel like it, from right to left, and be done with it. Now, outside of natural language, a lot of the data that we encounter actually isn't sequential, but it comes in different structures. And we have different architectures to deal with this kind of data. So two particular architectures to look at for this is convolutional neural networks, which people use a lot for image recognition. So this is for parsing an image and then extracting information from that. Like this is what Facebook will be using when you upload a photo and it says like, oh, is Mike on there and Susie. And then there's recursive neural networks, which you could sort of think of as a very language-centric variant of that kind of architecture. I'll very briefly talk about both of them. Going forward, let's start with the recursive neural networks. So here the idea is that instead of reading the text from left to right, we assume that we have some syntactic structure above that. So assume you have a syntax tree above that. And now instead of building up the state from left to right by reading one word at a time, we'll try to build up state from reading this tree from bottom to top. So like a super easy example for this would be some sentence like that. Tina likes tigers. That's the 3 words. And then we have some syntax tree on top there, which sort of takes the noun to a noun phrase, the object to another noun phrase, the verb together with that into a verb phrase, and then up there is the sentence, right? And now what you can do if you want to learn a representation of this kind of a sentence is you say we define a composition function that takes 2 inputs, like you did in a neural network, and combines them together. So like something super simple could just be that, right? You say the output of my representation is some nonlinearity applied to the sum of 2 weight times input vector multiplications. And you see that you can do this recursively, right? So as long as you make sure that y here is of the same dimensionality as sort of x left and x right, you can apply this function recursively as you move up the tree.
Anyone ever do that generatively?
That's the next slide.
All right,
And yeah, I mean, basically this is sort of a super simple composition function. If you want to think about it longer, you can also find ways to substitute this for a recurrent cell. This just gets a little bit more tricky now because you don't have just one initial starting state for your hidden representation, but you need to have several of those and you need to find ways of combining them as you move up. So in practice, it doesn't gain you much, except for sort of a bit of headache figuring out the math of that. But there's other nice things you can do with these things. So there's no simple generative counterpart, to answer your question, but it's possible to improve classifier training by using a bunch of different additional signals. So, I mean, here, if you just take this guy, the only signal we had, say if this is a sentiment classifier, is we compose all of this up, we have this final representation, we have our MLP, and we want to binary classify that sentence. And that's not an amazing signal if you sort of have a big tree, right? Most sentences are longer than Tina likes tigers. So what you can do to make this stronger is you can add something like an autoencoder signal, we say, okay, we compose two words together, we get this shared representation. And now in order to make sure that this shared representation actually captures both of these words, we autoencode this. So given that we have an inverse function that gives us sort of two reconstructed representations. So here, like you read in x1, you get this shared representation here, y1, which is a function of x1 and x2. And then from that, you have this inverse function that generates x1 dash. And now you put a loss on this where you say, well, I want x1 and x1 dash to be really close to each other. And by making sure that they're close to each other, we sort of end up running a compression function over the input space. This sort of helps regularize your training, give you a slightly stronger signal. I think that's all I'm going to say about recursive neural networks. I wouldn't massively recommend using them, but I did my PhD on those, so I had to put in at least 2 slides. Instead, what's more fun these days is you can look at convolutional neural networks. So these guys are mostly used, as I said earlier, in things like image recognition. So you have something like that where you start off with an image, and then you have these convolutional layers where you move a matrix across the image, like across all the little patches in the image, to calculate values in the feature maps. So each feature map here is the product of sort of a particular convolution applied to all possible strides in an input image. And then the second thing you can do is subsampling or pooling, where you sort of take a matrix of inputs and pool those into a single element. For instance, by taking the maximum, that's max pooling. There's also mean pooling and sort of additive pooling and other things. But that's basically all you do. So convolve, subsample, convolve, subsample, and then at the end you add this one fully connected layer that moves all of these feature maps into single vector representation, and we're back at a place with a vector representation, and we know how to classify with that. So these are really, really good for image recognition. And effectively, so to talk a little bit about what they're doing, is you have these convolutional windows that effectively work as classifiers for local features. So you could, on the highest level, say have this convolutional window that looks at a 3x3 box and takes these kind of weights. You have a component-wise product between the two of them. So this here, for instance, would give a really high value together with this particular feature map. A different square down here would give something near 0 because there's no overlap. And then what you do by stacking these guys up on top of each other is if you go from the raw image to having your first order local features, and you get higher order features, and eventually you end up at the prediction stage, where in this case you can predict what's the number that you're reading in this image. Now, they're really nice, right? The good thing with convolutional neural networks is they're crazy fast. You can stick all of this in GPUs and bam, it's crazy. They're super fast. Thursday, I think someone's going to explain this in more detail to you, Jeremy. Now, they're slightly funky with text, right? Because now you have to read text differently. They're not sequential in their nature. But then, what we learned from naive Bayes is actually bag of words representations are often sufficient for what we need. So maybe that's not so bad. And now, because you have these matrices that go over text, they actually take some degree of structure into account. So it's a little bit better than bag of words even as a representation when you want to think of CNNs for text. So that's the good things. The downsides is that they're non-sequential in their processing of input data. So you do end up losing some information. You don't have sort of this idea of building up state over time. You build up state over depth if you want to think about the analogy to an RNN. And it's easier to discriminate than to generate variably sized data. So if you think of a convolutional network for images, the standard assumption is that the input size here is fixed. Say this is like a 400 by 400 pixel image. And then we can do all of this, and we can also generate back again because it's easy to invert all of these processes. So we can say, okay, given a particular label, generate a new image. It's less clear how you would do this with generally variably sized data, something like text. So we can discriminate. If you want to generate, you need to think a bit harder about that. But let's just assume you want to go with it. This is roughly what it would look like if you stick a convolutional neural network onto text as a classifying mechanism. So think of your text as a matrix. Assume one dimension here is the input words, and the other dimension is the size of your input embeddings. So you get this kind of matrix here, which on the first level is actually just going to be a single matrix. And now what you can now do is just convolve them as if it were an image into many, many feature maps. And now the trick is here, those feature maps, we know how deep they are because that's a function of the input embedding size. But the second dimension here is variably size because that's a function of the size of your document. So the one trick you need to add to go from a ConvNet for images to ConvNet for text is you need to add max pooling over time. We just say, okay, no matter how long the document, we're going to split this into 20 segments, and so we'll just randomly divvy up the text into sort of 20 overlapping segments, however we need them, and then we max pool over these matrices. That's kind of the trick to go from variably sized data to fixed data. And once we're in fixed data land, then it's easy again, right? Because then we can get a vector, and then we can stick in the classifiers we talked about earlier. That's sort of all you need to know for convolutional neural networks. There's a tiny bit of the math here. Basically, there's two layers you need to think about. There's a convolutional layer and a subsampling or the max pooling layer. You'll also have a couple of other layers in Conference. When you look them up in literature, there will be nonlinearities, but they're component-wise, so they're easy to implement. The most interesting layer, I think, is the convolutional layer. So basically, you have this whole set of filters. And if you think about this in sort of image land, like a particular first-order filter could be, like, is this of a particular L shape, or is this of a particular circular shape in my image? And so what this is basically a dot product applied to the input data, sort of XL, where X is the input data at this particular level, together with a weight matrix, which is of the same shape as the segment that you want to export from that. And now there's sort of two or three important decisions to make when building a ConvNet. One is the number of filters you have. So this is how many different sort of features can we test for in a given level. The second thing is then the size of your filter matrix. That will sort of inform how big the features are that you can look for in a given pass. And the third thing is then the stride with which the filters move across the input. So for instance, if you had, say, an image of 100 by 100 pixels, you could say, okay, I want to have like a single filter of a 10 by 10 matrix, and I have a stride of 10. So I start off in the top left corner, and then I just move this guy along by 10 steps each way, and then down and across. So I go from sort of 10,000 inputs to 100 outputs. You could also have the same 10 by 10 matrix, and so actually with a stride of 1, I'll go across this, so you sort of just move right by 1 step each time, so you actually have all these overlapping input segments. And then you go from 100 by 100 matrix to a... Anyone? Me neither. Is it 90 by 90? 91 by 91? 90 by 90 matrix. Right? Does that make sense? Awesome. The other important layer is this max pooling layer. And max pooling layer is sort of the same idea, except that here we say we take this fixed size of input, and again we move across the input. So the bigger input matrix is the smaller matrix following a particular function. And then all we do in the max pooling case is say, okay, well, let's look across this, both of the image dimensions or feature dimensions, and we just take the maximum value. So that's a really easy function to implement. And again, both of these functions are super easy to backpropagate through as well. So that's one of the nice things about ConvNets, that once you have them in place, they're both very easy to implement and very easy to implement efficiently. So the actual math will actually look a little bit different. So you don't end up with dot products. You end up with matrix multiplications over time, and then you pull them together in a separate step, but that's just for efficiency purposes. I suspect that will get covered on Thursday's lecture, but otherwise, if you're interested, calculate it yourself. That's actually very straightforward. That's it. So that's it for text classification. Thursday, Jeremy's going to talk about GPUs, which will probably cover some aspects of the things we talked about today. And going forward, I'm coming back in a few weeks to talk about question answering, which will build a lot on the basic classifiers we discussed today. Yeah, there's a couple of papers that are worth looking at if you want to know more, but mostly actually a bunch of blogs that are really worth checking out, which give a nice summary of the kind of things we discussed today. I recommend you look at those. Thanks.